Hi, I'm Pushkar Shukla and today I'll be presenting our work CAVLI using image associations to produce local concept-based explanations. This is joint work done with Sushil, Bharati and Turk. Consider an image classification network. In this slide, we consider an image classifier where, given an input image, we want to predict whether the input image contains cows or not. In this work, we attempt to design a module that is able to provide local explanations that quantify the dependence of a decision made by an image classification system in terms of relevant human concepts. In this case, our focus is on developing a module that can analyze and understand the reasoning behind the classifier's decision regarding whether the presence of cows in the image is dependent on the fact that the background consists of grasslands. On a high level, our proposed approach can be broken down into three different research questions. The first question focuses on determining what parts of the image are significant for decision making. In this particular example, we would want to identify the portions of the image that are deemed most valuable by the classifier when making its determination that the image contains cows. Secondly, what parts of the image does the model associate most with the concept? Here, we want to identify parts of the image that the model deems most relevant or representative of grassland environments. Finally, once we are able to solve the two questions, we would want to measure the overlap between the two. A higher degree of overlap between image regions associated with decision making and image regions that are strongly associated with the concept implies that the concept has played a significant role in the decision making process, thereby suggesting a stronger dependency of the decision on the concept. We use the term image associations to refer to the overlap between regions in the that are associated with the concept and regions that are associated with the decision. Motivated by our intuition, we propose CAVLI that combines two popular yet orthogonal image explainability techniques, TCAV and line. Given an input image, we divide the image into superpixels and create k different images by randomly turning off some of the superpixels in the image. These images are then passed through the image classifier. To analyze the output vectors for a set of k images, a linear regression model is employed. These outputs are combined by binary vectors that indicate the activation or deactivation of patches in each of the k images. By incorporating these binary vectors as additional input variables, the linear regression model aims to establish the relationship between the output vectors and patterns of patch activation across the k images. The approach is similar to the LIME framework and results in a decision heat map indicating what superpixels are most useful for decision making. The second part of our problem focuses on understanding what parts of the image are most associated with a given concept. To solve this part, we train a TCAV with the same frozen backbone as the image classifier, but a different classification head to model a given concept. We then follow a procedure similar to step 1, where all the k images are passed through the TCAV module and the conceptual sensitivities are fit into a linear regression model. This can be thought of as applying LIME over the output of the TCAV model. This results in a concept heat map that assigns weights to different patches in the image depending on whether these patches are linked to the concept or not. Now, to solve the third part of the problem, we measure the overlap between the concept heat map and the decision heat map. We do this by proposing a concept dependency score that is the product of the conceptual sensitivity of the model and the correlation between the weights associated with the concept heat map and the decision heat map. The concept dependency score tells us about the dependence of a decision on a given concept. A higher value of CDS score indicates a greater dependence and vice versa. Here are some results. We select images from the class zebra in the ImageNet dataset and evaluate the average concept dependency score for 4 different concepts: stripes, grasslands, indoor, and horse on the inception net module. Our results show that the concept stripe has the highest CDS scores, whereas indoor backgrounds show the lowest CDS score. In addition to the previous analysis, we further conduct experiments involving different classification models specifically focused on the zebra class. These experiments aim to evaluate and compare the performance of various classification models in accurately identifying zebras. Furthermore, we also conduct experiments for the basketball class, specifically targeting the concepts of ball, jersey, gender, and race. We also conduct experiments on the Celeb A dataset. Here, we evaluate a smile classifier trained on the Celeb A dataset. We calculate the average CDS score for the attribute gender. The results show that the average CDS scores for females when they are smiling is much higher than all other class concept categories, implying that the model tends to associate the concept of female with the class smiling more frequently, even though there may not be a meaningful relationship between the two attributes. Our framework allows us to visualize the respective image associations by looking at the concept heat maps and decision heat maps to observe the commonality between regions useful for decision making and regions associated with a given concept. This allows the user to better reason about decisions and their concept dependence. To summarize our contribution, we propose a novel framework that combines two previously existing approaches to generate local concept-based explanations. Our approach attempts to measure the dependence of a decision made by an image classification system on a human-defined concept by utilizing image associations to provide explanations. Our framework also provides quantitative measures in terms of a CDS score and visual heat maps to explain the dependence of a decision of a concept. In the future, we plan to extend our work in different ways. We would like to understand the effect of using pixel-based weight assignment techniques over patch-based weight assignment techniques. Also, replacing attribution-based methods by attention-based mechanisms. In the longer term, we are also interested in the use case of association-based explainability methods like CAVLI, and would want to compare them to other styles of explainability methods like attention-based approaches or concept-based approaches. I would like to thank you for attending this talk. Do check out our paper and poster and feel free to contact.